So now that we've seen the eigenvalues of a square matrix A are the solutions to the characteristic polynomial, our goal is to use these eigenvalues to find the eigenvectors. So as before, we're going to require that A is a square matrix, and we're going to fix an eigenvalue lambda. That is, lambda is a solution to the characteristic equation. So we remember the eigenvectors associated to lambda are the solutions to the homogeneous equation a minus lambda I multiplied by v is equal to the zero vector. Stated another way, the eigenvectors associated to lambda form the null space of the matrix A minus lambda I. So, as you may imagine, if eigenvectors and eigenvalues are important, these null spaces are also very important subspaces of Rn. So we're going to give them a name. The eigenspace of A associated to the eigenvalue lambda is E sub lambda, which is defined to be the null space of the matrix A minus lambda I, which is of course a subspace of Rn. So to get some familiarity, let's work a couple of examples. So for our first example, we have the matrix A that we considered in our previous video. So A has the columns 1, 2, and 2, 1. We've already computed the characteristic polynomial for this matrix, and its factored form is lambda minus 3, lambda plus 1. We get two eigenvalues, which are 3 and minus 1. So to compute the eigenspaces, we take each of these eigenvalues one at a time and compute the matrix A minus lambda I. Let's do 3 first. A minus 3i is going to give us the matrix negative 2, 2, 2, negative 2. To compute the null space for this matrix, we first compute its reduced row echelon form. We can do this in 2 steps. First, by adding the top row to the bottom row, then scale the top row by negative 1/2. The top row of the reduced row echelon form tells us that the solutions to the homogeneous equation are exactly the line x minus y is equal to 0, or equivalently, x is equal to y. We can also think about this as the span of the single vector whose entries are 1, 1. So this is a one-dimensional subspace of R2, which is just the line y equals x. For the eigenspace associated to negative 1, we compute A plus I, which will give us the matrix with 2 in every slot. We can row reduce this also in 2 steps. First, subtract the top row from the bottom, and then scale the top row by 1/2. This tells us the null space of the matrix A plus I is the line x plus y is equal to 0. And of course we can express this as the span of the vector 1, minus 1. Now, these are our 2 eigenspaces. The first one was E3, which is just the line with slope 1 through the origin, and the eigenspace E sub minus 1, which is a perpendicular line also through the origin. So this tells us that we have a basis for R2 consisting of eigenvectors of our matrix A. So as another interesting example, let's consider a diagonal matrix. We're going to consider the particular diagonal matrix where all the entries along the diagonal are the same, and they're going to be 3. Now you can probably already guess the punchline here, but the process is somewhat informative. So we're going to compute the characteristic polynomial, which is the determinant of 3i minus lambda I. We can pull the I out on the right-hand side, so we see that the matrix 3i minus lambda I is also going to be a diagonal matrix, and the entries will be 3 minus lambda. The determinant, of course, is just 3 minus lambda squared. So there is a single root for the characteristic polynomial, which tells us we have a repeated eigenvalue. To compute the eigenspace, we take the matrix A, which was 3i, and we subtract 3 times I from it. Unsurprisingly, this gives us the matrix 0. And of course, the null space of the matrix 0 is all of R2. Well, that just means A times V is equal to 3V. But we already knew this. And as before, it is clear that there is a basis for R2 consisting of eigenvectors of the matrix 3i. Namely, you could always choose the standard basis. So these first couple of examples might lead you to conclude that every matrix has a basis of eigenvectors. Unfortunately, this is not always the case. So here is an example to disabuse you of that notion. So we'll take a matrix which is almost, but not quite diagonal. It's upper triangular, and it has the same entry, 2, along the diagonal. We can compute the characteristic equation, and as before, we have a single repeated root, lambda is equal to 2. If we compute the matrix A minus 2i, then we'll see, unlike the previous example, we end up with a single non-zero entry. This, of course, tells us that the matrix A minus 2i has a one-dimensional null space. And that null space is the line y equals 0. And of course, we can write this as the span of the vector e1 and simply recognize this as the x-axis. So we do not, in this particular case, get a basis for R2. So next time, we're going to explore the behavior of repeated eigenvalues in more depth.